Hi, good morning, everyone. Good morning. Thank you. One question I had given you for homework yesterday. Yes? Have you completed it? Good morning, good morning. Those who missed the class yesterday, did they go through the recording? Yes? Right. Fine. There's a question I asked you to do. This was a homework question. A capacitor. Right. First, let's try to slightly recall what we did yesterday. What is capacitance of a capacitor? Charge over potential difference between the plates of the capacitor. Okay. Charge over potential difference is the capacitance. Capacitance is measured in what? Farads. Good. So charge is measured in what? Coulombs. Voltage is measured in what? Volts. So now if you take a capacitor, okay, if you take a capacitor, and if you charge it, if you give it more and more charge, what will happen to its voltage? What will happen to its voltage? Will also increase. When you increase the charge, voltage will also increase. What will happen to its capacitance? It won't change. Capacitance won't change. Correct? So that is when you charge a capacitor. So can you keep on charging a capacitor forever? No. Why not? There is a maximum capacity that it can take. So after that point, it won't charge. Correct? So when a capacitor is discharging means what? Giving the charge out. So when a capacitor is discharging, the charge stored in it will decrease. Capacitance of it will remain the same. Voltage will decrease. How is the relationship between voltage and the charge? Directly proportional. Do you remember that graph? Voltage versus charge graph is a straight line passing through the origin with a constant gradient. Can you remember the other graphs that we did? For charging of capacitors and discharging of capacitors, we did two sets of separate graphs, the charge versus time, current versus time, voltage versus time. Okay, fine. And then we came up with this equation, Q equals Q naught e to the power minus T over RC. That RC product is known as what? Time constant. Very good. So that the same equation is there for voltage and current as well. Right. Question 2. A capacitor has a charge of 200 millicoulombs. Capacitor has a charge of 200 millicoulombs stored in it. It has a capacitance of 20 millifarads and connected across a 100 ohm resistor. Calculate the initial voltage across the capacitor. So for the initial voltage, I can use Q equals CV. Q equals CV. Initial charge stored is 200 millicoulombs, which is 200 into 10 to the power minus 3. C is 20 millifarads, which is 20 into 10 to the power minus 3 into the V. So V equals 10 volts. Initial voltage. Initial voltage across the plates of the capacitor is 10 volts. Then the next one, voltage across the capacitor after 1.5 seconds. I can use V equals V naught e to the power minus t of RC to find the voltage after 1.5 seconds, which is initial voltage is 10 e to the power minus after 1.5 seconds t is 1.5 over the resistor across which it is connected is 100 ohms into C is 20 millifarads. 20 millifarads is 0.02 farads. Okay, that will be 10 into e to the power minus 1.5 over, is it 4.72? So after 1.5 seconds, the voltage across the capacitor will be 4.72 volts. Okay, have you got this answer? Part C. Charge stored in the capacitor after 1.8 seconds. So we can use for charge now, Q equals Q naught e to the power minus t of RC. So initial charge is how much? 200 millicoulombs. So 200, I will take it as 0.2 coulombs. E to the power minus t is 1.8 seconds. Over the R is 100. C is 20 millifarads, which is again 0.02. Okay, that will be 0.081 coulombs. 0.081 coulombs. We had got it in millicoulombs, it would have been 81.3 millicoulombs. Okay, if we had left this 0.2, what I took it in coulombs, if we had taken it as 200 millicoulombs, your final answer will be in millicoulombs, you would have got 81. Okay, right. The next one, total charge passed through the resistor in the first 1.8 seconds. What is the answer for that? 0 point? Right. Now here's it, guys. Initially, the capacitor has a charge of 0.2 coulombs. Originally. Okay. After 1.8 seconds, the charge stored in the capacitor is remaining in the capacitor is 0.081 coulombs. Okay. So the difference is the charge which is released by the capacitor, right? In the first 1.8 seconds. Yes or no? Initially, there is 200 millicoulombs, 0.2 coulombs. After 1.8 seconds, the charge remaining in the capacitor is 0.081 coulombs. So during that 1.8 seconds, what is the charge released by the capacitor? That is the question, right? Total charge passed through the resistor in the first 1.8 seconds. That is indirectly they are asking you how much the charge capacitor has released in the first 1.8 seconds, which is going to be the difference between the two values, 0.2 minus 0.081. That is 0.119. Is that okay? Sorry. Okay. Any questions, anyone? Right. Why do you all look like some sleepy faces? What time do you wake up on Sunday? Huh? What time did you wake up? 4:30. Sure. What time did you sleep? You? Oh, wait, I confused with that. You woke up at 7:30. What time did you sleep last night? That's a lot of sleep. Right. There's part E. Initial current passing through the resistor. So for the initial current passing through the resistor, I will use V equals IR for the initial stage. What is the initial voltage across the capacitor? 10 volts. The initial voltage that is supplied to the resistor is 10 volts. Okay. And equals I into what is the resistance? Resistance is 100 ohms. So I equals 10 over 100, which is 0.1 ampere. This is the initial current. Agree? Current through the resistor after 2.1 seconds. Now we can use I equals I naught e to the power minus T over RC.
Can you go back for 1 second, please?
Okay. Right. The current through the resistor after 2.1 seconds. Initial current I naught is 0.1 into e to the power minus T is 2.1 over R is 100, C is 0.2, right? Which is going to be 0.1 into e to the power minus 2.1, 0.035 amperes. Have you got these answers? Have you? Sorry? Current is 0.1, it is about minus T is 2.1 over R is capacitance is 0.02. Oh. Correct, but I have taken 0.02 in the calculator. Okay, now? Any questions? Now, before I go to the next part, I need to talk a little bit of maths. A little bit of maths. Have you all done logarithm? I mean, the math students? Yes. Can someone explain me what is log? Those who have done log, can you tell me?
Something related to base and power.
Something related to base and the power. Guys, listen. I will give you what is relevant for you all related to log. Now, guys, you know what is 2 to the power 3? 8. No. Now, there is another part of another area of maths which is known as log, for those who have never heard about log. Okay. So if 2 to the power 3 is equal to 2 to the power 3 is equal to 8, then the same representation, now this is a representation of 2 to the power 3, 2 into 2 into 2. A representation of 2 into 2 into 2 is 2 to the power 3. Okay. 2 to the power 3. 2 to the power 3 means 2 into 2 into 2. So 2 to the power 3 equals 8. The same thing that we can represent in the log form, which is log 8 to the base 2 is equal to 3. log 8 to the base 2 is equal to 3. So this power comes here as the answer. This is the base of the log. Okay. So this 8 is here. So log 8 to the base 2 is equal to 3. If I take another example, 2 to the power 5 is equal to 32. Then we can write it log 32 to the base 2 is equal to 5. Okay. Then another example, if I take 5 to the power 2 is equal to 25. Then log 25 to the base 5 is equal to 2. Okay. So what if I tell you a to the power b equals c? How can we put this in the log form? Log c to the base a equals b. Okay. Those who are not doing math, can you quickly take it down? Okay. Right. Then because now I told you E is a special number. Let's say e to the power x equals y. E to the power x equals y. Can you tell me this in the log form? Log y to the base e equals x. Correct? E is just a special number. So e to the power x equals y means log y to the base e equals x. Now this log y to the base e is there. No? For that is represented as ln y. So ln y equals x. This log y to the base e can be written as ln y. Okay. So for an example, if you want log 5 to the base e, that is written as ln 5. If you want log x to the base e, that is written as ln x. Understood? Take down this also. I'm only talking to you the little that you need to know about log. So this doesn't cover the entire log. I'm just telling you what you need to know. Okay. And then there are three interesting rules in log. It's good for you to have an idea about it. One is known as a power rule of logarithms, which means, let's say you have ln or log x to the power a. This can be written as a times ln x. This is you call the power rule of logarithms. This a can come in front. So a comes in front, it becomes a into ln x. And there is this product rule of logarithms, or the multiplication rule. That will be, don't write, listen. Whereas if you have log a into b, okay, if you have log a into b, that can be written as what? Log a plus log b. If it is ln a into b or log a into b, that will become log a plus log b. Okay. Then one more, division rule or the quotient rule of logarithms, which is log a divided by b will be equal to log a minus log b. Okay, take it down. Right. Guys, I'll do a few examples. Look at this. Let's say you have log x to the power 3. You can write it as 3 ln x. Okay. Let's say you have ln y to the power 5. You can write it as 5 ln y. Okay. Let's say you have ln 3x. You can write it as ln 3 plus ln x. Product rule. Okay. Let's say you have ln 5a. You can write it as ln 5 plus ln. Correct. Let's say you have ln y over 3. You can write it as ln y minus ln 3. Let's say you have ln 3x to the power 5. You can write it as ln 3 plus ln x to the power 5 in the first stage using the product rule. Because 3x to the power 5 means 3 into x to the power 5, right? So you can write it as ln 3 plus ln x to the power 5. And then ln 3 using the product rule here, the power rule here. You can make it 5 ln x. Correct. Take it down with an understanding. Don't just copy. Right. Now let me take you again to the 3 equations we learned. I'll take this one. Q equals Q naught e to the power minus T of R's. Correct. I will take ln on either sides. Then this will be ln Q equals ln Q into e to the power minus T of R's. I'm taking ln on either side. You can do that in any equation. If you are doing the same thing for both the sides, that's totally fine. Okay, so we have the equation Q equals Q naught e to the power minus T over RC. I'm taking ln on either side, same. Okay, so ln Q equals ln this entire thing. So which is ln Q equals, I'm going to use the product rule here, which is ln Q plus ln e to the power minus T over RC. Okay, which is ln Q. This power minus T over RC will come in front. Power rule. So it will be minus T over RC into ln E. What is ln E? Log e to the base E. What is that? 1. ln E is 1. Log e to the base E. E to the power 1 is what equal to E. So that means this is equal to 1. Okay. So then you get another format of the same equation, which is ln Q equals. This is Q naught, sorry. ln Q equals ln Q naught minus TORC. This is another format of the same equation. Okay. Yes. Understood? Take it down. Can you take the log of a negative number? Does ln minus 5 exist? No. Why not? Fine. Not relevant. Do it. So guys, then obviously you can do this for the other two as well. Then similarly, if you take the voltage variation, ln V equals ln V naught minus T over RC. Current variation will be ln I equals ln I naught minus T over RC. Is that okay? Take it out. Right? Right. Guys, rather another question. A capacitor has a capacitance of 200 microfarads. Capacitor has a capacitance of 200 microfarad, and it is fully charged. It is fully charged using a 20-volt battery. Full stop. Then it is discharged by connecting it to a 150 kilo ohm resistor. 150 kilo ohm resistor. Full stop. Calculate part A. The initial charge stored in the capacitor. The initial charge stored in the capacitor. The initial charge stored in the capacitor. Part B. The charge stored in the capacitor after 18 seconds. Volt charge stored in the capacitor after 18 seconds is part B. Part C, voltage across the capacitor after 20 seconds. Voltage across the capacitor after 20 seconds. Part D, time taken for the voltage. Time taken for the voltage across the capacitor to reduce to 7 volts. Time taken for the voltage across the capacitor to reduce to 7 volts. Part E, initial energy stored in the capacitor. What gives the energy stored in the capacitor? Half VQ. Part F, and I also told you there are 2 more equations and we did questions on that, correct? Part F, energy stored in the capacitor after 18 seconds. Energy stored in the capacitor after 18 seconds. Part G, energy stored in the capacitor after 20 seconds. Give a try. I'll give you 3 minutes. Yeah, you can. Okay. No need.
Sir,
Hmm?
so whenever we want, we can use log or we can use the normal formula, right? There's no
Correct.
difference.
Yeah, you can use both. Okay, enough, no? I'll do it. Hope you're done. Right, capacitor has a capacitance of 200 microfarads and it's fully charged with a 20-volt battery. Then it is connected to a 150 kilo ohm resistor and it will be discharged. Part A, the initial charge stored in the capacitor, Q equals CV. C is 200 into 10 to the power minus 6. V is 20, which is 4 into 10 to the power minus 3 coulombs. Am I right? 4 millicoulombs, correct? Part B, the charge stored in the capacitor
Sir,
after, yeah,
someone wants to show. Someone wants to show question number E.
okay. The charge stored in the capacitor after 18 seconds, we can use Q equals Q naught e to the power minus TORC. So initial charge is 4 into 10 to the power minus 3 e to the power minus T is 18 over RC. R is 150 kilo ohms, C is 200 microfarads. That is 115 to 10 to the power 3. 200 into 10 to the power minus 6. Okay. That will be 2.20 into 10 to the power minus 3 coulombs. This is the energy stored after 18 seconds. Sorry, this is the charge stored after 18 seconds. Okay. Voltage across the capacitor after 20 seconds. Initial voltage is 20. What did others get? 2.19, that's 2.20. Check it. So V equals V naught e to the power minus TORC. Initial voltage is 20. E to the power minus T is 20 after 20 seconds. R is 115 to 10 to the power 3. C is 200 into 10 to the power minus 6. That will be 20 into e to the power minus 20 . 10.268, that's 10.3 volts. The voltage after 20 seconds. Right? Have you got this answer? Right, part B. Time taken for the voltage across the capacitor to reduce to
For this,
7.
it's better to use log, right?
Correct. The time taken for the voltage to reduce to 7 volts. So in this case, it's easier if we can use ln V equals ln V naught wait a minute, guys. Okay. So in this case, Hi. When did you come? Just now? What? You leave the car at 9. Last time? You didn't think he said it? Sure. Okay, right. So guys, in this one, we'll use LNV equals LNV naught minus T over RC. Okay. So we are taking the time. We are checking the time taken for the voltage to reduce to 7. So it will be ln 7. And the initial voltage is what? 20 minus T over RC. What is the 150 kilo ohms?
So 150 to the 10 to the power 3. And then
Into
200 times 10 to the power minus 6.
200. 10. From here you can find the T. So guys, 150 into 10 to the power 3 into 200 into 10 to the power minus 6 will be 30. So ln 7 equals ln 20 minus T over 30. Bring the minus term to the left, it will be plus T over 30 equals ln 20 minus ln 7. From here we can get the T subjected, which is ln 20 minus ln 7 and multiply it by 30, which is 31.5 seconds. Huh? Correct. What is the initial voltage? No. This V in this equation is the new voltage. Okay. New voltage is 7. V naught is the initial voltage, which is 20. So when you put that into the feed it into this equation, the T gives you is the time taken for the voltage to reduce from 20 to 7. Done.
So I have to
Time taken for the voltage across the capacitor to reduce to 7 volts. So the time taken for the new voltage to be 7. Yeah. Wrong. Wrong. It doesn't work like that. You have to take for the time taken for the new voltage to become 7. So V will be 7. Okay. Right. Guys, the initial energy stored in the capacitor will be equals half VQ. Half, what is the initial V? Do you know the initial Q? 0.10 to the power minus 3. So 20 into 4 into 10 to the power minus 3. How much is that? 0.04. correct? And energy stored in the capacitor after 18 seconds. After 18 seconds, I know what is the charge, right? In part B, we have calculated the charge after 18 seconds. So since we know the charge after 18 seconds, I can use E equals half Q square over C. Since I know the charge. Okay.
So we know the voltage also, so why can't we use E is equal half QE?
When did you find the voltage?
Didn't we?
When did you find the voltage? Did you find
After
it?
20 seconds we found.
That is for 20 seconds. So we are calculating the energy stored in 18. That is half. There's a Q after 18 seconds is.
So once again, what about question number E?
Huh?
Once again, so I didn't do question number E, so once again. Can you go to E, sir, please?
Okay. Right. So half Q square over C. Q is 2.2 into 10 to the power minus 3, and that's square. And what is the capacitance? 200 into 10 to the power minus 6. Are you getting 0.0121? Okay. Yes. And then the last one. To find the energy stored in the capacitor after 20 seconds. After 20 seconds, we know what? We know the voltage, which is 10.3. So I'll use half CV square. Equals half CV square. So half C is 200 into 10 to the power minus 6. V is how much? 10.3, and that needs to be squared. Zero point 0.0106. Is that okay? Any questions, anyone? Shall I take the tip? We'll do 2 questions and take a break. Take the tube. We'll come back to that slowly. There's enough questions for us to do from this. Yeah. Let's turn to question number 3. Can you give it a try? Okay, the first part A will answer together. A student was investigating capacitors and set up the circuit shown. He has put a circuit. The student planned to use a circuit. The student planned to use a circuit to measure the PD V across the capacitor C as it was charged and discharged through the resistor R. Okay, now his target is his plan is to measure the potential difference across the capacitor when it is charging and when it is discharging through the resistor R. That was his plan. Okay, do you think he did it right? No. What are the problems you see? One is the resistor is on the wrong side because it is in series with the battery. Okay. So when the capacitor when the switch is connected to X, voltmeter is not going to measure any voltage. Okay. When the switch is put to Y, R has no business. The voltage, when it will be discharging, but not through the resistor. Okay, it will be just discharging through these connecting wires and the voltmeter. So in that
Voltmeter reading will be wrong.
voltmeter is not going to measure the voltage across the resistor. It will be just measuring the voltage across the capacitor. Okay. So they're asking you, give two reasons why the circuit did not operate as intended. One is, yes, tell me your answer. Resistor is connected in series with the battery. In series with the battery. Okay. The next one I would say, while charging, voltmeter is not connected to the circuit.
So, but then is that a mistake or I don't know. How is that a mistake?
Now,
It
what
is,
was his,
used to
what was
calculate the voltmeter like after discharging from the resistor, right?
no? But he was planning to do what? What was his intention? The student planned to use the circuit to measure the potential
Oh,
difference across the capacitor C as it was charged and discharged. That was he wanted to do. So,
so how
while
is he supposed to do that?
uh,
How is he supposed to do that? Where is he
maybe,
supposed to put the voltmeter?
maybe he could have used two different voltmeters, one for charging and
Yeah.
one for discharging. Right.
So if
Anyway,
it is
let's
a
see.
second voltmeter, where should he put it?
Maybe what he could have done is,
No, no,
one
if it
thing
is a second voltmeter, where should he put it?
on either sides. Maybe we could have he would have could have come up with a circuit like this. We have a battery here. Okay. And he should have definitely put the other resistor here. And he could have had a voltmeter to measure the voltage here, V1, and another voltmeter, maybe here, V2. This is using 2 voltmeters. Okay,
Yeah, thank you.
right, let's do the part B and C. Sorry, there's no C. B has 3 parts, give it a try. Hmm. Okay, anyone got the answer to the part one? Yes. What is your answer? Okay, we'll do it. Here you guys look at this one. Now, the initial, when the switch is put to Y, okay, the discharging is happening. So the voltmeter, the student moved the switch from position X to Y. The student recorded the values of V as T increased when the time is increasing and plotted the graph of V versus T. The capacitance of the capacitor is given 2.2 microfarads. Determine the resistance in the circuit when the switch was at position Y. Okay, listen. First tell me this. When it is at position Y, to what we see, there is no resistor. But they're talking about the resistance. That is the resistance of what? The wires, the connected wires. And could be this voltmeter can be having a resistance as well, a small resistance. All that put together is the resistance they are referring here, not the resistor. Okay, right. Determine the resistance in the circuit when the switch is at position Y. Guys, what is the initial voltage you see? 6.2. So the V naught is 6.2 volts. What are the capacitance? 2.2 10 to the power minus 6 farads. So I'm going to use ln V equals ln V naught minus T over RC. Okay. ln V equals ln V naught minus T over RC. Take another point which is definitely not closer to this initial point, but with clear coordinates.
45 and 1 is better. 45 and 1, sir. The best.
45
I
and
think.
1. But it looks
45
like
seconds and 1. It looks slightly, but then.
it slightly looks
Or you
lower.
can take 40. So 40 and. No,
Isn't
but-
25 and 2.2 perfect? Out of the points available, for me, 25 and 2.2 looks perfect. It's perfectly passing through that point. Huh? 30 and 1.8 is also okay. So I'm going to choose this point. So when the T is 25 seconds, V is 2.2 volts. Put that data into this equation, we are going to get the answer. ln 2.2 equals ln 6.2 minus 25 over RC. I'll take it as RC. I'll find the RC product and then substitute for the C. Okay. So guys, I'll bring the minus 25 over RC to the left. It will become plus 25 over RC. 25 over RC is ln 6.2 minus ln 2.2. So the RC product will be equal to 25 divided by ln 6.2 minus ln 2.2. Correct me if I'm wrong. I'm getting 24.129. 24.129, that is my RC product. Okay. Then the C is 2.2, R into C is 2.2 into 10 to the power minus 6 is equal to 24.129, which is going to be R equals 24.129 divided by 2.2 into 10 to the power minus 6, which is 1.1 into 10 to the power 7 ohms. Is that okay? This question is from the 2023 January paper.
So for part 2, sir, should you take a tangent?
Let me check, wait. So guys, 2023 January paper, those who have the market scheme, you can check the answer. Part 2, determine the average current in the circuit between t equals 0 and t equals 30 seconds. Average current. Right. What can we do about that? Like, listen to me. From 0 to 30, the average current in the circuit. The easiest thing what we can do is, we can find, we know, or we can find what is the charge stored in the capacitor at t equals 0. And then we can find the charge stored in the capacitor at t equals 30. That difference will give you how much charge released from the capacitor in the 30 seconds. That divided by 30 will give you the average current. Yes or no? Current is the charge released over time taken, right? Charge over time. So if you know how much charge is released from the capacitor in the 30 seconds, then you can find the average current. Current equals charge over time. For marker, there will be a little bit of work. Do it. I have told you the steps. Give a try.
$1.8.
Don't look at the screen, do your work, get the answer. Don't copy what I'm doing.
So how did you get that equation?
Wait. There are few people who are trying it. I will explain it after that. So can you also use the equation finding the initial current and final current, and yeah, that is also you can find initial current and final current, add them and divide by 2. But the thing is, it will not be exactly the same value. Can be slightly different. This is more accurate than that. Because if you get the initial value and final value and then divide by 2, the variation in the current is not a linear variation. So that will not give you an accurate value. This is more accurate compared to that. Okay. Right. Guys, I'm getting 3.2 into 10 to the power minus 7. Anyone who got this answer? Good. Let me explain you what I have done. Just like what I told you at the very beginning. I use the graph, and using Q equals CV, I found initial charge stored in the capacitor. Okay. Now you should understand this business, guys. Listen, look at this. Let me explain. Look at this circuit. When you put this, the moment you switch this, put the switch to point Y. Initially, this capacitor is now charged. No, the fellow has charge with him. Okay. So once you put the switch to Y, what he will do is he will give the charge out. He's giving charge out. He is distributing charge. Okay. So initially he will be, initially I found at t equals 0 how much charge he is having by using Q equals CV, which is 1.36 into 10 to the power minus 5 coulombs the capacitor has with him at t equals 0. Okay. Then I did the same thing by using the graph. At t equals 30 seconds, I use Q equals CV to see how much charge there in the capacitor when t equals 30. Clearly the charge has reduced. Obviously. Why? Because he was giving charge out. Okay. So the charge has reduced. So how much charge did the capacitor put out? That is the difference between these two values. So the charge passing in the circuit in this 30 seconds is discharge minus discharge. The difference. So that difference is what I have written here as delta Q. So I wrote it as an equation. Current is, guys, rate of flow of charge. No, grade 9 physics. Rate of flow of charge. So the rate of flow of charge is the charge flowing over the time taken. So the charge flowing is the difference between the above two values that we have got. This minus this. That divided by the time is 30. Done. Okay. Any questions? Right. The next one, part 3. Calculate the energy dissipated by the current in the circuit between t equals 0 and t equals 30.
So we should find the energy at 0 seconds and energy at 30 seconds, right? And then minus the answer and we get the energy.
Correct. That's right. You're right. Okay. How? Why? No. That average that you're getting is, now here the Q is the charge remaining in the capacitor. This Q that I have calculated 3.96 into 10 to the minus 6 is the remaining in the capacitor. So what is the point in getting the average of what is remaining in the capacitor? Current is the charge which is flowing out over the time taken. So you need to know how much charge going out, not what is remaining in the capacitor. Get it?
So I'm just asking, but so can't we make a tangent between 0 and 30 seconds and then find that?
Which one?
For part 2, for the average.
You're talking about this graph.
Yeah.
Anyway, this graph is, the tangent is not going to work. The reason is, this is voltage and this is time. So the tangent is going to give you V over T. Current is not V over T.
Yeah.
Yeah, if you had the graph of Q versus T, then yes. Okay. Right. Because I'm getting 3.87 to the power minus 5. Joules. Are you getting this answer? So what I did is, at t equals 0, I used E equals half CV square. C is 2.2 into 10 to the power minus 6, V is 6.2 square. Did the same thing for t equals 30, half CV square. V is 1.8, and got the two E1 and E2 values and get the difference. Is that okay? You need a break, right? Yeah, I also need a break. Let's go for a break. See you in 15 minutes. And we'll come back and start with question number 7. Have you started the seventh one? Hi people, hello. Welcome back. Start with the seventh one. The student built the circuit given below. The capacitor was initially uncharged. She closed the switch and plotted a graph of current on ammeter A1 against time. Determine whether the initial value of the current on the graph is consistent with the value stated in the circuit diagram. Sorry. Guys, according to the graph, the initial current is 0.15 milliamperes, right? Somewhere around 0.15 or maybe slightly,
0.155.
yeah, slightly bit more than maybe 0.15. Okay. According to the figures given in the diagram, if I use V equals IR, initially at T equals 0, the moment you closes the switch, the entire 5 volts will be across this 33 kilo ohms. Then it will be, if I use V equals IR, V is 5, I into DR is 33,000. So I equals 5 divided by 33,000, which is 1.5 into 10 to the power minus 4 amperes. Multiply that by 1000 to get it in milliamperes. 0.1515 milliamperes. Or 0.152 milliamperes is what I'm getting. Okay. I have got it in milliamperes.
So yeah, it's correct.
Yes. So the conclusion is, determine whether the initial value of the current on the graph is consistent with the value stated on the circuit diagram. Yes. It is consistent.
So aren't you supposed to state the value in the graph?
Huh?
Aren't you supposed to state the value of the graph?
Yeah, if you want, I don't think it's necessary. It's obvious from 0.
So necessary, right? Yeah.
Yeah, not necessary. When you say it's consistent. Right, guys, can you continue the question? There are parts up to E. I'll give you 5 minutes, give it time. Right. Okay. Guys, explain how the current on the ammeter A2 would vary over the same time interval. What do you think? How will be the variation of the ammeter A to B? Will it be the same as the A1 or will it be
No,
different?
it will be slightly higher, right? Because there's less resistance.
Hmm? It'll be the same. Why? Because they are in series, no? In a series circuit, the current is the same everywhere, right? So I would say it's the same thing. You can write. It will be the same as ammeter A1 since both ammeters are connected in series. Okay, right. Determine the capacitance of the capacitor. Guys, what if I will take a point again on this graph, a well-known point. I will take this point, okay, which is when the time is 19, the current is 0.01, correct me if I'm wrong, okay, when the time is 19 seconds, t is 19, current is 0.01 amperes.
So why can't you take 1 ampere, sir? Isn't it better?
You mean here? This one?
No, 0.1 ampere, sir.
Yeah, 0.1 milliampere
Yeah,
you're talking.
yeah, milliampere, sir, sorry.
Yeah, that should be
And
okay.
then you can take 0 and 30, right?
0 and 0 and
30 seconds.
this one. That is not really, because it
Why,
might
sir?
have 0 even before 30. Because even if you take 28, it looks like 0. Even at 27, it's 0. So it's better not take the 0 any value before that. Okay, it's not easy for you to judge exactly when it comes to 0. So the initial current is how much?
Initial current is 0.152, right?
I will take 0.15, a bit more than 0. Here, no? I'll take 0.153. Okay,
So but when when you use the calculations, you found 153, right?
give me a minute. I notice 0.153. Now these are in milliamperes at t equals 0. Okay, so it will be I will use I equals ln I equals ln I naught minus T over RC. Correct? This is the equation, which is ln 0.153 into 10 to the power minus 3. No, 0.01 into 10 to the power minus 3 equals ln 0.153 into 10 to the power minus 3 minus T is 19 over RC. The R is 33 kilo ohms, 33,000. Anyway, I'll take it as RC. So from here, if I get the RC subjected, the RC I'm getting 6.965. So the C will be 6.965 divided by the R. The R is 33 kilo ohms. 2.11 into 10 to the power minus 4. Farads is what I'm getting. I have the market scheme answer. Market scheme has given a range. They have accepted anything between 2 into 10 to the power minus 4 to 2.3 into 10 to the power minus 4. Okay. So no worries if you are getting anything in that range, 2 to 2.3, anything is fine. Is that okay? Guys, the same question, I will try with a different method and see, but don't get confused. Huh? Are you all done with this? Are you all done with this? Any questions with this, anyone? Okay, right. Now, since there's a small confusion here with the initial current, since we don't know the exact thing, I would like to do this one. Okay, look at this. I'll try this and see what I'm getting. Okay, stop your work. Listen to me. Guys, now it's obvious that at t equals 3, current is 0.1 milliamperes, right? That's an obvious thing now. And also another obvious thing is at t equals 90, current is 0.01 milliamperes, right? Agree? See, I'm doing this because we are not very clear about the initial current is not an exact value. There's a small confusion there, right? I will use the equation between these two. Okay. Taking this says t equals 0. This says t equals 60. Okay. I will take this as the initial point. Then this becomes t equals 60, 19 minus 3. Then look at this. ln I equals ln I naught minus t over RC. ln 0.01 into 10 to the power minus 3 equals ln 0.1 into 10 to the power minus 3 minus t is 16 over RC. If I get the RC product, it will be 6.9487. So the C will be that divided by, what is the R? 33,000, which is 2.105 into 10 to the power minus 4 farads. What did we get? 2.11. That means the estimation that I made as the initial current as 0.153 is a very accurate estimation. Do you understand what I'm saying? Here we got 2.11 into 10 to the power minus 4. Here I am getting 2.105 into 10 to the power minus 4, which is very, very close. Okay. If you want, take it down. I just want to let you know you can do it this way as well.
Sir,
Mhm.
I understand why you took T3 as your initial T equals 0, but then why do you have to convert T19 like into T16? Because anyway, it's a point, right?
Yeah, but the T equals 3 is I'm taking as the initial point. No? This is my initial point, right? So from that point to this point, it's only 16 seconds, right? You look at this graph, the time from here to here is 16 seconds.
Understood, yeah.
Yeah, any questions you can ask me, you can ask me. Tell me. Tell me. Okay, done. There are two more parts. Part D, determine the charge stored on the capacitor after 30 seconds. After 30 seconds. Because after 30 seconds, the current has become 0. Okay. Current has become 0 means, that means the capacitor has become fully charged. Agree? You are using the battery to charge the capacitor. So you charge, while charging, the charging current will reduce, and then eventually you can see the current has become 0. So why did the current become 0? As I told you earlier, capacitor has become fully charged. It can't take any more. Okay. So indirectly, what are they asking? The charge at 30 seconds means they are asking you, when the capacitor is fully charged, what is the charge stored? Am I right? So which will be Q equals CV. Capacitance is how much? 2.11 into 10 to the power minus 4. And the voltage supplied by the battery is 5 volts. So that will be the voltage across the capacitor when it is fully charged. Which is 1.06 into 10 to the power minus 3 coulombs. One point zero, yeah, correct. So to 2SF, it is 1.1 into 10 to the power minus 3 coulombs. So once again, they have given a range in the market scale. Determine the maximum energy stored in the capacitor by the capacitor. So that is when the capacitor is fully charged. Once again, I can use E equals half CV square or half VQ. So if I use half CV square, half into C is 2.11 into 10 to the power minus 4. And the V is 5 square. Maximum energy stored is when the capacitor is fully charged. Okay, that will be 2.64 into 10 to the power minus 3.
Sir,
Yeah.
doesn't the capacitor have any resistance?
Huh?
Doesn't
get
the
you.
capacitor have any resistance? You muted me, sir.
Capacitor has any inbuilt resistance.
No, because when things are in when components are in series, don't you have to divide by the voltage? Divide the voltage.
Can you please tell me? I mean, I didn't get your question.
No, when components are in series in a circuit, they don't have the same voltage as in the battery, right? Like
No,
in
no.
parallel.
Listen. How it works is, listen. Initially, the current is coming from the battery, it passes through this, it goes through this, and this capacitor gets charged. Listen to me carefully. Once, while it is getting charged, the current will reduce. Okay, reduce. That means the charge stored in this capacitor is increasing. And once this capacitor is fully charged, listen, once the capacitor is fully charged, when it is fully charged, the current in the circuit is 0. There's no current. There's no current means the voltage across this resistor will be 0. Voltage across that resistor is 0 means the voltage across the capacitor will be 5 volts. Understood? So when the capacitor is fully charged, at that point, the entire 5 volts is across the capacitor. Okay? Is that clear?
Yes, thank you.
Okay, let's say, okay, one last thing for the day. While it is charging at a given time, let's say maybe the time was 5 seconds or something. During that time, let me say, I'll take 3 seconds. The current is 0.1 milliampere. Listen to me carefully. 0.1 milliampere. So guys, if I use V equals IR for this resistor, I is 0.1 into 10 to the power minus 3. The resistance is 33 into 10 to the power 3. At that time, this is 3.3 volts. This voltage is 3.3 volts. Okay. At that moment, if you see the voltage across the capacitor, it will be 1.7 volts. Because the battery has 5 volts. Understand? So during this process of 0 to 30 seconds, what is happening for the voltages across the resistor and the capacitor is, voltage across the resistor will keep on decreasing. Okay. Voltage across the capacitor will keep on increasing. When you initially started at T equals 0, the resistor had a voltage of 5 volts. Capacitor had a voltage of 0. Eventually, when T becomes 30 seconds, resistor becomes 0 volts. Capacitor becomes 5 volts. Understood? Is that clear? Right. So guys, I won't be meeting you next week. So we will be meeting again the first week of September. And I have enough work for you. Please mark this. Right? Question number 9, 10, 18, 20, 21, 26, 'That's it. So have a nice week. Or
So very little, sir. You said lots
enough.
to keep us busy. Not enough.
Okay. See you. See you in 2 weeks. Bye. Take care.
Thank you, sir.
Welcome.